Figure number 1 shows a solenoid, and solenoids are nothing more than a cylindrical winding of wire with the windings very tightly packed. So in this example we're shown the direction that current is flowing. So if you use the right-hand rule and model the direction of current flow with your fingers, I think you'll see that the north end is here and the south end is here. In other words, the solenoid has magnetic field lines passing through it, and it behaves as a dipole magnetic field, and the north and the south end are determined based on right-hand rule. Now, figure number 2 shows what happens if the coils are spaced farther and not as tightly packed as they are in figure number 1. In that case, some of the magnetic field lines can stray, and there's a reasonable amount of magnetic field outside compared to the magnetic field inside. Figure number 3 shows the coils packed a little bit tighter once again, and so there's some small amount of magnetic field somewhere outside the solenoid, but the field is certainly much greater in magnitude at points inside. Well, in this lesson, we're going to use Amperes Law to come up with an equation that expresses how strong the magnetic field is at the points inside of the solenoid. Now, we're going to restrict ourselves to this region because we notice as you get toward the open end of the solenoid, the magnetic field becomes less uniform, but in the interior part of the solenoid, the field is rather uniform. So Amperes Law is the alternative method to the law of Biot-Savart for determining magnetic field, and we can get away with using Amperes Law in the case where there's some symmetry to the problem. It says that the closed loop integral of B dot ds is equal to mu naught, the permeability of free space, multiplied by the amount of current enclosed by some Amperian loop. So the trick is to make sure you're picturing your Amperian loop clearly. So let's draw a solenoid. And along with drawing your Amperian loop, you should have some rough idea of what the magnetic field lines look like. So the magnetic field lines are a bit non-uniform near the ends of the solenoid, but as the field lines continue through and emerge out the other side, in the interior, the field lines are pretty uniform. Okay, so if the current is flowing in the correct direction, then the magnetic field lines will point to the right. So the Amperian loop I want to picture is rectangular. And I'm going to choose an Amperian loop about that long. And my rectangle is half in the solenoid and half out of the solenoid. It has a length of L, a width of W. And then I'm going to break up that whole loop into little bits. So there's a portion of the loop right here that I call ds. There's another ds, and another ds, and another ds, and ds. So I'm breaking up the whole perimeter of this rectangle as a bunch of little segments that I call ds. So there we go. I've pictured my ds. I have a picture of what the field looks like. And for me to add up the product of b and ds all the way around the loop, and I guess I have to add up on what I'll call this side A, B, C, and D. Okay, so the total amount of product of magnetic field and path length would be B dot ds along path A plus B dot ds, keep in mind these are vectors, along path B, plus B dot ds along path C, plus B dot ds along path D. Okay, well, let's see. For parts, how about let's do B and D first. So if there is any magnetic field, as weak as it is on the outside, there is some magnetic field at points outside of the solenoid. But any field is going to encounter this side and this side. So the field is pointing directly to the left, but ds is either pointing up or pointing down. So the angle between B and ds in parts B and D of my Amperian loop is 90 degrees. So what I have is B ds cosine 90, B ds cosine 90. But cosine 90 is 0, so there's no product of magnetic field and displacement along either of those paths. And then we'll say that for part C, this side, there is a product. The magnetic field points this way. ds points in the same direction, but the field is so weak out here compared to the interior of the solenoid that we'll say for this part the magnetic field is practically 0. So really, to find the total amount of product of field and path length, I just need to calculate the portion of it along side A of my Amperian loop. So we have B ds cosine of 0 degrees in this case, right? ds points to the right, magnetic field line points to the right, so angle is 0 degrees. So I need to take the integral of B ds cosine 0 from 0, say x equals 0, up to x equals L. And that's equal to mu naught times the amount of current enclosed. Now, how much current is enclosed? So if we say there's a current I that flows through the solenoid, it flows down and then into the page and then up and then out of the page and then down and into the page and up and out of the page. Okay, so here we go. None of it has passed through my Amperian loop yet until right now. The current passed into the loop. And then again 2 times. And then the current passes into the loop a 3rd time and a 4th time. So the current, I don't know, the current passes in, I'll just say n number of times. All right? So the amount of current enclosed is a multiple of the number of windings enclosed by my Amperian loop. So I've enclosed more than one winding. So this is mu naught n times capital I. Okay, well, the b comes out of the integral sign. Cosine of 0 is 1. So b times the integral of ds from 0 to L equals mu naught capital N times I becomes BL equals mu naught capital N times I. So this means the magnetic field is mu naught times N over L times I. Now, the question comes up, then it changes. If I were to go through that derivation one more time, my answer changes depending on how big I make my Amperian loop, right? In the first case, our Amperian loop was about this wide. So what if I tried again and I make an Amperian loop that's this wide? Now, as long as I don't go too far to where I'm near the ends where the magnetic field is non-uniform, that should be a valid Amperian loop, and we'd get the same result. The integral of B dot ds is mu naught times I enclosed. This is a complete loop integral, so I get a product as I go from x equals 0 up to x equals L along path A. There is no contribution along path B or D, and practically 0 along path C. So this all just comes out to B times L equals mu naught. And now you see I've captured a greater number of windings in this longer Amperian loop than I would have in a shorter loop. So if N changes depending on my Amperian loop, then how can I get a consistent answer? Well, you probably see that not only did N change, but L changed as well. And so the ratio of N over L is a constant. So we get B equals mu naught, capital N times I over L. If we want, we could restate that as B equals mu naught times the quantity N over L times I. So N represents the total number of windings or turns. We can introduce a new variable, lowercase n, which is like the density of windings. In other words, the number of turns per centimeter, or the number of turns per meter, or whatever length you choose. So then we can say B equals mu naught times lowercase n times I. And lowercase n doesn't change regardless of the size of my Amperian loop. Whichever form of this equation you prefer, they both represent the same thing, and those are both the result that we get by applying Amperes Law to a solenoid. And so let's review how many different paths for current we have an equation for. We know the magnetic field at this point at a distance of r from a long straight wire. We actually did this solution both ways. We used Bios of r and we used Amperes Law, and we got the same thing in both cases. We find that the magnetic field, as long as r is much, much less than the length of the wire, the magnetic field at this point is equal to mu naught I over 2 pi r. We used the law of Bios of r to find the magnetic field at the center of a single loop of wire, and we found that B equals mu naught I over 2r. Then we turned that loop on its side, and we found the magnetic field at this point is equal to mu naught I times, what is it? Times r squared divided by 2 times x squared plus r squared to the 3/2 power. We said if we wind that around several times, then that just increases the magnetic field by a factor equal to the number of windings. So n times mu naught I times r squared over 2 times x squared plus r squared to the 3/2. And we imagined, what if we had 2 of these coils separated by a distance equal to their radius? We called that a Helmholtz coil. We found in that case B equals mu naught I over 5/4 to the 3/2 power times r. So here we are with yet another arrangement of current. Call it a solenoid, and the magnetic field for a solenoid is mu naught n over L times I, or mu naught lowercase n times I. In the next video segment, we'll determine what the magnetic field is for a solenoid that's been bent around into a complete circle. We refer to that as a toroid.